Yesterday's class continuation part. So yesterday we had discussed about the oxidative ozonolysis and reductive ozonolysis. Just I'll revise for 1 minute. Oxidative ozonolysis, it is done with the Ag2O or H2O2 with ozone. So oxidative ozonolysis of alkenes always gives carboxylic acids. So it's plus carbon dioxide plus ketone, depend on the type of the molecule we select. Reductive ozonolysis. So reductive ozonolysis of alkenes we carry out in the presence of the zinc H2O, or else we can take the dimethyl sulfide. We get only carbonyl compounds. So these are the generally products what we expected and we got in yesterday's reactions. But apart from that, there is one more molecule which gives same carboxylic, one more reagent which gives the same carboxylic acid just like the oxidative ozonolysis, that is H plus KMnO4. So I'll write down here note. The products in the oxidative ozonolysis and H plus KMnO4. If you use H plus KMnO4 in the presence of the water are same. So I will take the molecule, one or two examples I will take, so you can understand the concept here. See, there is a molecule C2H5 and CH3 here, C double bond CH3. So now you use ozone Ag2O, or else you can use H plus KMnO4, not OH minus KMnO4, H plus KMnO4. So the products are always same. Carbon, this forms keto part, and if any CH is there, hydrogen is there to the double bonded carbon atom, that becomes the carboxylic acid. So CH3COOH. Let's take some 2-3 molecules also with the same combination. CH2, CH double bond CH2. So just you put the H plus KMnO4, then you will get the CH3, CH2, COOH plus CO2. H plus KMnO4, keto part with CO2. So you might have understood by now that how the CO2 is coming, how the COOH is coming, how the keto part is coming. So I'll give a summary of this particular part. It is simple thing that if any double bonded carbon atom is having some alkyl group R dash and R, if it is subject with the ozone in the presence of the Ag2O or H2O2, or else if you use H plus KMnO4, this particular, because this carbon is having the two alkyl groups and double bond, it will be converted to the keto group. And if any alkene is like this type of the groups, if any this type of the groups are there, since hydrogen is there, so oxidative ozonolysis as well as the H plus KMnO4, they convert that particular alkene part to the carboxylic acid. This will be. and if any terminal CH2 is there, and both of these reagents will convert this terminal CH2 to the carbon dioxide. Okay. So only final example I will take, and we shall start the another question. CH3C, I am giving an example, CH3 double bond, CH double bond CH2, you can see now. Okay. So use these reagents. Since this particular area is having double bond carbon with 2 alkyl parts, so this particular carbon will be converted to this particular carbon will be converted to the keto group. And here double bond carbon atoms are having the hydrogen. So they will be converted to the carboxylic acid. And this is a double bond carbon with 2 hydrogens. So this part will be converted to the carbon dioxide. So when you write down the product, you will get these molecules. Do not by heart this reaction, just understand the concept. COOH, COOH plus CO2. So this is the reactions. In this way you have to write down the reactions. Okay. So now I'll give some examples, and okay, let's complete the even alkane parts also. One of the important part is what happens if alkynes undergo ozonolysis. You must remember one important thing. This is a very important part, you have to remember that. Alkynes on ozonolysis, it may be reductive or oxidative. Whatever the ozonolysis it may be, alkynes on ozonolysis gives carboxylic acids. So whether you are using the reductive ozonolysis or oxidative ozonolysis, it is none of it our business, just write down the carboxylic acids. So in that, this particular group RC triple bond will be converted to the using any of these reagents, that means ozone, or else use the H2O2, or else Ag2O, or else dimethyl sulfide, any of these parts. They just convert a triple bonded carbon. 1 minute. This triple bonded carbon having no hydrogen. So I will write here triple bonded carbon without hydrogen will be converted to the carboxylic acid. Okay, so I will write down that product simply COOH. And what happens if a triple bonded carbon is having the hydrogen? Means just like this. Use this one. So now I will write the part that this is the triple bonded carbon with hydrogen will be converted directly to the carbon dioxide. There double bonded CH2 converted to the carbon dioxide in the case of the oxidative ozonolysis, but not in the reductive ozonolysis. But here a triple bonded carbon with hydrogen will be converted to the carbon dioxide. So we shall see some examples which will be very helpful for us. You just see here CH3, C triple bond C, CH2 and CH3. Just take ozone, you take H2O2 or Ag2O or dimethyl sulfide, whatever it may, zinc H2, whatever it may be. This particular area will be disconnected and giving the carboxylic acid from both of these double bonded carbon, triple bonded carbon atoms. So we get the CH3COOH plus CH3CH2COOH, that I am writing like this, CH3CH2COOH. Okay. Now we shall take one more molecule, CH3, CH2, C triple bond CH with any of these reagents, so that again this will be COOH part, and this particular carbon will form the carbon dioxide. So the molecule what we are going to produce here is CH3, CH2, COOH plus CO2. So you must understand the basic concept behind of this one. You have to use only this particular dimethyl sulfide. Then the question arises, sir, what happens if zinc H2O is used? That is the note point. So here the note point is alkynes on ozonolysis is the important point with zinc H2O gives diketones, means triple bonded carbons will be converted to the ketones. I will give that example. Here you may ask the question, sir, here you put the reductive ozonolysis. Reductive ozonolysis with dimethyl sulfide. So dimethyl sulfide is also acting as the oxidative part. Okay. Or else you can remove that particular part, you consider this one as reductive ozonolysis and simply say that dimethyl sulfide also gives the product like oxidative ozonolysis. So I'll take one particular molecule, CH3, C triple bond C, CH3 is important molecule, not the reaction. So just you take the ozone, zinc H2. So we get this CH3, both of these double bond, triple bonded carbon atoms converted to the C double bond O part, diketones. Means only pi bonds will be broken, not the sigma bond. So this is the advantage of these two reactions. So I will mention here that Me2S also gives the oxidative ozonolysis products. Simply that, and here I will mention that also acts as oxidizing agent. Now I will give some questions so that you write down the product for these questions, which is very helpful to understand the concept. So the questions are, first of all, the question is, give the products that you expect from the following reactions. Okay, so I'll give some products here. The question is, first question, CH2, ozone, H2O2. Second one is O3, zinc H2O. O3 dimethyl sulfide. H plus KMnO4. Heat it. Sometimes even they mention as OH minus also. You consider it as OH minus. I will tell the difference later. But actually only acidified KMnO4 gives, not the OH minus KMnO4. OH minus KMnO4 reactions are a bit different. But even though some people they give OH minus KMnO4, you just follow the H plus KMnO4 like products. even for the OH minus KMnO4 also. So this is the product. I request you to answer these questions. I will give the answers for these questions now. It is an oxidative ozonolysis. This part will become ketone and this CH2 part will become carbon dioxide, and this is reductive ozonolysis. Okay, so that just disconnect the bond and put the oxygens both the side, so that we get the molecule like this. This is one keto part and other one is double bond O hydrogen, aldehyde, and this is also reductive ozonolysis. Just disconnect the bonds. See, I am not writing a separate molecules again, I am writing like this. So disconnect the bond here and here. So here you put this particular carbon, you put the double bond O and hydrogen. Here also you put the double bond O and hydrogen, plus this top part. Top part will be converted like this, double bond O with hydrogen, double bond O. So this is the molecule. Even if you connect them, you will get the same molecule back. H plus KMnO4. So H plus KMnO4 main purpose is to disconnect the bonds. It just convert the double bond, triple bond to the carboxylic acid only. So that you just write down COOH, COOH, and here again oxidative ozonolysis. So this becomes COOH, COOH, this one COOH and COOH. So let us see oxidative ozonolysis products. One, two, three. Here also 1, 2, 3. So actually we expect the aldehyde, but aldehyde immediately converted to the carboxylic acid. This is H2O2 is there, except zinc part, remaining all ozonolysis gives this one carboxylic acid. So just disconnect this one. You get this CH3, CH2, COOH plus CH3, CH2, COOH, means two same molecules. So these are the products what actually we get in the in these reactions. If any doubt is there, you can ask me. If no doubt, we shall go to the next part. Let us see polymerization and addition with HNO3, addition with acetyl chloride, all these. Addition with HNO3. Just I am writing the reaction and product, and this is much discussion is not required in this particular case. Just see the reaction, how the reaction is going to happen. HNO3 can be written as HONO2. So that OH one side and O2 other side. CH2OH. CH2NO2. And similarly, let us take the acetyl chloride. Addition of acetyl chloride. CH3COCl. So one side chlorine, the other side CH3CO plus, actually this is. So that positive part goes to the double bonded carbon with more number of hydrogens. So CH2Cl one side and CH2COCH3. This is the another one. So here polymer reactions, let us see. I just only introduce polymer reactions, polymerization. Actually, we shall discuss the rest of the entire thing in the polymers chapter. Here, whatever is important, that we shall discuss. First of all, poly stands for many. Mer stands for the units, or some people may call it as the molecules. So polymer is the combination of the many molecules or many similar units. So if you see, I have taken this ethylene molecule. If this ethylene molecule is added with another ethylene molecule in the presence of certain reagents, I will explain that reagents also, what type of reagents it may be. That reagent may be cation, or it may be anion, or it may be free radical. Okay. So if the polymerization reaction happens in the presence of the cation, it is called as the cationic polymerization. If it happens in the presence of the anion, it is called the anionic polymerization. If it happens with the free radical, it is called the free radical polymerization. So they have their own names. So here this pi bond shifts this side and this pi bond shifts this side. If any other molecule, that pi bond shifts like that. And this molecule get the pi bond from the another molecule which is placed this side. So we get the molecule finally like this: CH2, 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 and it continues like this. Okay. So in this process, have you observed one thing, that the same CH2 is getting repeated? How many times it will get repeated? The number of times repeated of this particular unit is equal to number of molecules we are taking here. If you take 2 times it will get repeated. If you take 3 times it will get repeated. If you take n times it will get repeated. Okay. So in this particular process, the unit, the basic unit we used for this reaction is called the monomer. The molecule that repeatedly repeated in the reaction is called the monomer. And because of the repetition of the monomer, we are getting the long chain molecule which is called the polymer. Okay. So regarding the cationic, anionic and free radical polymerization, I'll just give an example here. So you just see CH2 double bond CH2 n times I have taken. Just use some catalyst H plus or Lewis acids like boron trifluoride, any of these molecules you can use it. So if you use, what happens, this cation initially attacks over these pi electrons. So these electrons will be shifted here and this particular one gets the positive charge, CH2 positive charge, and it becomes CH3. So this will not sit quite because n number of molecules are available now. So that's why the same cation, whatever is formed from the initial step, that will start acting as a catalyst for the next reaction. Now it is also positive one, just like here. Now this positive one attacks over here and this one attacks over here, so that you can see how the length of the molecule is going to be increased. CH2 CH2, next CH2 CH3, and this will attack on over another ethylene molecule. So that you will get another long chain molecule, CH2 plus CH2, 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 CH2. You can see you have to count the number. Why? Because it must be even number, because here even number of carbon atoms are there. 1, 2, 3, 4, 5 are there. So that 1, 2, 3, 4, 5, sixth one is the CH3 part. So it will continue like that. Then when to terminate this reaction? The termination happens if any other negative charged part is added. Some like B minus, a negative ion is added. So negative ion will attack with the positive ion and it will get neutralized. So both ends will get neutralized. But in this process, if you see, this particular one is getting repeated all the time. Hence it is called as the polymer. Okay. So here cation initiate the reaction, so it is called the cationic polymer. Then what happens in the case of the anionic polymerization? I just take an example that anionic polymerization, you see CH2 plus, okay, I'll take this one n number of the times. You just take Cn minus. So the Cn minus attacks over here and the electrons will go over the other side because already electron is just the positive electromeric effect. This is the negative electromeric effect. So the molecule is now CH2 minus CH2Cn. And this negative charge now will attack on another alkene molecule. Okay, it will attack like this and it will go there. So that it will continue, this process will continue till all the alkene parts got over. Okay, so it will continue like this. And in this one, this is getting repeated. So here we put the n number of times. Since anion initiated this reaction, we call it as anionic polymerization. Then what about the free radical polymerization? Free radical polymerization means free radicals will initiate the reaction. See, CH2 double bond CH2, use some peroxide. Peroxide means RO radical will be there. So again we will get the CH2, no polymer mentioned with the complete formula, like this only they will mention. The same monomer unit they will take, the pi bond they will break, they put on both the sides, this n value go here. Okay, so let us see how the mechanism takes place. A simple mechanism I will explain. CH2 double bond CH2 plus, this is a free radical. So free radical is not having the positive charge, not having the complete electrons, only single electron is there. So it needs one more electron to form the bond. Hence these pi electrons undergo homolytic cleavage, so that another free radical will be produced, and here one more free radical comes, that free radical forms the bond with this one. So we get the molecule like this, and this molecule will not sit quiet, it participate in the reaction with another alkene molecule. Okay, again homolytic cleavage, so that we get the CH radical, CH2, this will be connected to this radical, next to OR. So this process will continue to take place till all the alkene parts are over. So this is called the free radical polymerization. Now there is a good reagent which we use in the polymerization reaction is, that is Ziegler-Natta catalyst. Ziegler-Natta catalyst. What is this Ziegler-Natta catalyst? It is simply that trialkyl aluminum. So you take 4 alkyl groups, aluminum combination, titanium tetrachloride. This is called as the Ziegler-Natta catalyst. Name I will write down. Sorry, not 4, 3 alkyl groups. Trialkyl aluminum, titanium tetrachloride is called as the Ziegler-Natta catalyst, and the person, because of the invention for this catalyst, he got the Nobel Prize, because this particular catalyst reduced many steps in the polymerization, so that it saved the so much of the time, energy, money, everything, so that the polymers become so cheaper, and nowadays we are getting the polymers and plastic material for so much of cheap cost. Okay, so now let us see certain type of the polymers. Only some polymers I will take and rest I will not take here, because polymers chapter is there we shall discuss. If an alkene, this is, what is this alkene? This is ethene or ethylene. Both names we call ethene is the IUPAC name. If it undergo polymerization, we just write down the polymerization. We don't mention the conditions generally, or else you can write down the Ziegler-Natta catalyst. Don't write Zn catalyst. They may think that this is again zinc. I am just writing. So it undergo n number of molecules and we get the CH2 n number of the times. It is the polymer, right? It is the polymer of which molecule? Ethene molecule. So for the poly you add ethene. Name is polythene. Or else for the poly you add ethylene. Polyethylene. Polythene covers. You have seen, no? So its molecular formula is this one. Similarly, I'll take one more polymer. Many are there. We'll take only few polymers here. That is CH2 CHCl. This is called as the vinyl chloride. N number of the times. If it undergo polymerization, then you may ask the question how this will come out. Simple, this pi bond will shift this side. So that we have to write down the molecule CH2, CH, Cl, CH and put the bracket like this and N. You must remember that while mentioning the certain bonds, these bonds must be out of the molecule. You have to show bonds like this. It means that the polymer chain is this side and this side it continuously present, repeated. And bracket and N means the same unit is going to repeated n number of the times. Okay, this is the vinyl chloride. This is the polymer of the vinyl chloride. So that you just see poly, you write down this name here again, vinyl chloride. Its very shortcut name is PVC. PVC pipes. Whatever you are seeing nowadays, its formula is this one, polyvinyl chloride. So we shall take one more. These are all similar names, and let us take n number of the times CH2 double bond CH. In the place of Cl, you take cyanide. It is called as acrylonitrile. Acrylonitrile. So this acrylonitrile, if it subjected to the polymerization in the presence of FeSO4 plus H2O2, so that you will get the molecule CH2, CH, Cn, and it will continue to take place like this n number of the times. And the name again, so that you know, poly, add this name here, acrylonitrile. It is popular known as PAN, PAN, polyacrylonitrile. It's commercially, this polyacrylonitrile, commercially it is called as Orlon. It is also called as the Orlon, or sometimes it is called as the acrylon. This Orlon, acrylon or PAN or polyacrylonitrile, this is mainly used in making of the clothes, carpets, blankets, means particularly clothing material. Okay, now let us see one more polymer. CF2 double bond CF2. Okay, this is called the tetrafluoroethene. N number of the times you take, again subject to the polymerization at a high temperature and pressure, high pressure. Generally the catalyst is NH4 taken twice S2O8. So here you will get the, just write down the pi bond outside. So you will get the CF2 gives in the sense bond. Don't again you also call it as a gives. So now the name of this molecule is poly. Just write down this name here again. tetrafluoroethene. So PTTFE. So simply we call it as a PTFE. But popularly it is known as Teflon. Teflon coating, you might have seen that most of the utensils. So whatever the utensils are there, utensils means nowadays what we call non-sticky coating materials are coming. There they mentioned Teflon coating. That Teflon coating formula is this one. This is the Teflon. Okay. So it's a chemical material in polymer. So that whenever you keep on putting some hard materials while washing, so here so whenever the hard materials you are using, that hard materials will immediately remove this Teflon coating, so that the Teflon coating comes out along with the food materials, and some material may be washed out during the washing process and some may not. So in such cases, whatever the unwashed material is there, if you use the same that vessel for the cooking purpose, then automatically it will be mixed with the cooking food and it will go into the body. So that these whatever these non-sticky materials are, they are not at all good to use. So now let us see this some substitution and interest reactions. Substitution reaction. These reactions indirectly we have discussed, but even though we shall discuss once again. I have some throat problem. Substitution reactions. So usually we say that alkanes participate in the addition reactions, but alkanes participate even in the substitution reactions, but in the presence of certain conditions. For example, if you take some alkene, CH double bond CH3 is there. If this is subjected to the, I will write three reactions here, so that you can understand very clearly which is the substituent reaction and which is the normal reaction. So that in the substituent reactions, halogenation is the only important reaction, so that I am going to discuss about the halogenation only. So during the substitution reactions, during the substitution, SR means substitution reactions, substitution takes place at allylic position. All these substitution reactions are free radical reactions. So I will take one example here. That example, very interesting example, CH2 double bond CH3. So this is you just subject with chlorine H2O, subject with chlorine CCl4 and chlorine around high temperature 500 degrees centigrade. So you might have observed three different combination of the reagents we are using. See, when water is used, chlorine reacts with the water and forms HOCl. Chlorine with the CCl4 no reaction, so chlorine as it is will go and add to the both the double bonded carbon atoms. Chlorine with 500 degrees centigrade, whenever they mention the temperature without these solvents, then put the chlorine on the allylic position here, not here. So the products what we are going to get here is HOCl dissociates into OH minus and Cl plus. Positive part of the reagent will be added to the double bonded carbon with more number of hydrogens. So we get the molecule CH2Cl, CH, OH, CH3. This is the what, and second one is CH2Cl, CH2Cl and CH3. These two are addition reactions, and temperature is used so that it goes and attack over the allylic position. This is allylic position, so that double bond will not get affected. So this is a very important reaction. You must remember, not reaction, a procedure is very important. how the reagent is going to attack in a particular molecule with a different type of the solvents and temperature. So this is one combination. The second combination is, we have already discussed that N-bromosuccinamide. So just take any alkene and add N-bromosuccinamide. Simply we say that NBS. This was already discussed. It mainly attacks on the allylic position and it introduces bromine on the allylic position. So I do not want to discuss much about this reagent once again, as this was discussed. You can see our previous videos. Okay. So now let us see very important part of alkenes is oxidation reactions. You must be very careful about the oxidation reactions of alkenes. What are the reagents? What about their properties? So first of all, I will not explain the reactions directly. I will pick up each and every reagent and I will explain their properties so that you can understand what products you are going to get. So first one is cold dilute alkaline KMnO4. It is also called as the Bayer's reagent. And second one is osmium tetroxide, O4 osmium tetroxide, with the combination of, you can take the NaHSO3 or else, this is or not both, Na2SO3, either bisulfite or directly sulfite, or you can use H2O2. This is one oxidizing agent towards the alkenes. And third one is, you just take the H2O2 hydrogen peroxide and carboxylic acid, that means formic acid. And fourth reagent is iodine with CH3COOAg, silver acetate. So these are all a different type of the reagents. And fifth one is H plus. See here, alkaline means OH minus, alkaline in the sense OH minus. Here we are using H plus. So H plus KMnO4, or you can use the K2Cr2O7. This is one oxidizing agent. And the sixth one is, you can use HiO4 or else you can use, means HiO4 and other characteristics are same, so that I am using, why to use with the HiO4 I will take separately. Seventh one is lead acetate. Eighth one is, means these three are same almost, properties are same, NiO4. And apart from this, there is one more, PdCl2 plus H2O. Now our duty is, what is the use of this reagent and how they convert the alkene part, means double bonded carbon atom, like this double bonded carbon, means you always imagine this is how they are going to convert this alkene part. See, Bayer's reagent, osmium tetroxide, H2O2, iodine acetate and H plus KMnO4, all these, not H plus KMnO4 up to here, first four reagents. First four reagents converts the double bonded carbon atoms like alkenes to their respective OH groups. If two OH groups are placed on the side carbon atoms, these are called as glycols. So this all gives the glycols. Their stereochemistry is different. Stereochemistry, if it comes to the stereochemistry, then Bayer's reagent, osmium tetroxide will add, I am writing here, this follows syn addition, means both OH groups comes and add on the same side, and this is anti-addition. Addition means anti-oxidation actually. Anti-oxidation. Again this is syn oxidation. Okay. Now let us see what is the use of this H plus KMnO4 or not. H plus KMnO4 and H plus KMnO4 and K2Cr2O7 properties separately I will discuss it down. Let me complete these remaining HiO4 and all these. Okay. So in this particular one, let us come with this particular palladium chloride. It converts double bonded carbons to the aldehyde plus a ketone. If both are having the hydrogens, it forms the aldehyde. If anyone is having the double bonded carbon with one more part, it gives the ketone part. I will give that examples also. And here NiO4, HiO4, whatever are there, this NiO4, lead acetate and all these products are similar to this one. So this particular area is of same category. So what about their category in this sense? Please note down carefully. Double bonded carbon with CH2 is there, it will convert to the carbon dioxide. Okay. And RCH double bond part will be converted to the RCOOH. And RC double bond R dash, similar concept we have discussed, converted to the keto part. All of these reagents properties are same. So hope you understood these particular reagents. So now one by one we shall start understanding the how to apply these concepts to each and every of these one, even stereochemistry also, so that you just see. First with Bayer's reagent. So I'll write down, because if you read this particular area, that will be fine. So I'll write down here cold dilute alkaline KMnO4 is called as the Bayer's reagent. You take this molecule, use the alkaline KMnO4 H2O with this cold, you have to mention it, oxygen, or else directly you can take H2O2, so that you will get the CH2OH, CH2OH. This is called as ethane 1,2 diol or ethylene glycol. Okay. So now let us take another molecule. I will choose another color so that it may be good for me. CH3, CH double bond, CH2, same reagent, put OH groups here. Okay. Now let us take another one. This is the cis alkene and cold dilute alkaline KMnO4. So what product you are expecting? I said here clearly that it is giving the syn addition, right? So already we have taken this cis alkene. Cis alkene with the syn addition gives meso product. So the product will be meso product. CH3. This is CH3, hydrogen OH, hydrogen OH. So that you do not get confused, sir, how meso product has come. This is the molecule is the cis molecule, and the reagent what we are using that undergoes that attacks from the same side. Means syn addition with the cis always gives the meso compound. Okay. Now I'll take one more molecule. CH3, CH3, hydrogen, hydrogen. Now it is a trans one. So cold dilute alkaline KMnO4. It is a syn addition again. So the cis plus trans means you will get the racemic mixture. Both combinations are possible. CH3, CH3, HOH, OHH plus its mirror image. CH3, CH3, OH, hydrogen, hydrogen, OH. So these are the racemic mixture. 50% is that component, 50% is this compound. So racemic mixture will get, that means is nothing but enantiomeric mixture. Okay, and let us take one more molecule. This is syn addition. This is also cis compound. Now you can understand the stereochemistry what I am going to write down here. Just put both the OH groups on the same side. And write down both the methyl groups above the plane of the ring. So in this way we are going to get the molecule. The important thing is what is the use of this reaction. It has many applications, many in the sense one important reaction is there. That means note point Bayer's reagent. Bayer's reagent is cold dilute alkaline KMnO4, which is a pink color compound. So Bayer's reagent on reaction with unsaturated compounds, not alkene, not only alkene, unsaturated compounds, it may be alkyne or alkene, it will be decolorized. It will be decolorized. So this is helpful in identifying the presence of the unsaturation. So we can say that thus this reaction is used as a test of unsaturation. Okay. So in the coming class, next session, we shall discuss about the osmium tetroxide. 1 minute. It is not moving. Yeah. Osmium tetroxide is, so from about all these reagents, we shall discuss in the next session.